Wait, I thought she
Okay. The AP practice problem from yesterday, realized looking at it that there's mentions of one-sided limits and we haven't gone over that. We're not going to get to that till next week, so I'm going to come back and reassign that sometime next week. So today we're going to talk about evaluating limits algebraically. We talked about graphical, finding limits graphically, looking at those arrows from both sides, seeing if they are in agreements. And then we looked at table of values, which was looking at the y values. And can we see that the y values are approaching the same number from both sides? So today we're talking about if we had just the algebraic expression in front of us without the graph, can we still find limits without the graph? So let's look at page 5. And let me go through some notes and then we can do some practice. Okay, so here's first rule. Limit as x approaches c of b is always equal to b. So let's say, well, b is just a constant. So let's say we had a graph that was like y equals 3. It doesn't matter if we're approaching 5 or 6 or 8 or 9. Your y value is always holding at that y value of 3. It's never going to change. So if you're looking at a constant, that constant is basically a horizontal line, and that horizontal line is never changing. So your limit is always just going to be that horizontal line, right? Limit is the y value. So it doesn't matter if we're approaching from the left or from the right. If it's just a horizontal line, that y value will never change. Okay. Now, if we're dealing with an algebraic expression, we're going to just basically do direct substitution method to begin with. So to find limits for a function, first try to evaluate the argument in the expression. We just plug in the value. Just pretend like you're finding the y value of a function and seeing what you get. If you get a real number, then there's nothing more to do. It's if my graph is continuous, it doesn't matter. My order pair and my limits is going to feel like it's one and the same. No change at all. So if the resulting value is a real number, we stop because that value is our limit. So let's look at some of those examples, kind of like those easier examples. But this is also an important step because sometimes when we get to more complicated problems, we may feel like we can just ignore the step. But you always want to do this as your first step. Always, if you see a real number, if it's approaching a real number, we always want to do direct substitution because that's also a way of gathering information because you don't have the graph in front of you, but by doing direct substitution, you can look at the number you get back in return, and that number, whether it is a real number or not a real number, can help guide what your graph is looking like. Okay. All right, so first things first, we're going to evaluate the limits of our expression. This is approaching a real number. Eventually, we will talk about approaching infinity or negative infinity, so we have a different set of steps for that. But if it's approaching a real number, we always do direct substitution. Okay, so we just plug in 2 and pretend like we're just finding the y value and see what we get. So if I plug 2 in for x, what do we get for our expression? Okay, 2 squared plus 3 times 2. That's our result. All right, 4 plus 6. 10, yeah. And that's a real number, right? So there's nothing more to do. Limit as x approaches 1 of our expression 3x to the fifth power minus 2x squared plus 7x plus 4. Direct substitution, let's see what we get. All right, try that. You guys get -8. Next up, limit as x approaches 2 of 5. Do we have any variables to plug in? No. So what do we get? Just what? Just 5, yeah. So imagine this is just a horizontal line at y equals 5. Doesn't matter if we're approaching 2 or 5 or 8 or -6. That y value is never going to change. It's just going to hold steady at 5. Okay, limit as x approaches pi of x cosine of x. Replace every x with pi. Okay, so now we just think unit circle values, right? Pi times cosine of pi, that will give us a real number. Cosine of pi is what? Close. -1, yeah. So pi times -1 is negative pi. Negative pi is a real number. So okay. This is not meant to be challenging. This is more of kind of like the first step that we need to take. Okay. If we get a real number, we stop. If we don't get a real number, then we have more things to do. But we never want to skip this step. Even if you feel like you know what's coming up, we always want to do direct substitution as our first step. Okay, so that's important. So what if we don't get a real number? Right? If we don't get a real number, sometimes the limit still exists. Okay. So we always want to evaluate the argument first, like we said before. So we plug in our value into our expression. If we get a real number, then great. That's our answer. But if we do direct substitution and if we get 0 over 0, then that's basically what we call indeterminate form. So I'm going to highlight that here. If you get 0 over 0, that means that there is a hole in the graph. Which means that the graph may look something like this. And what did we discover yesterday? If there's a hole in the graph, if the graph looks like this, does the limit exist? Yes, because if I pick points on either side of my target, my arrows are going to head towards the same y value, and the limit does exist. But we're going to try to do this without looking at the graph. So the algebraic way of telling us that there's a hole in the graph is seeing that 0 over 0. So if you see 0 over 0, you know that the point doesn't exist, but the limit does exist. We're going to find the limit, which haven't found it yet. The limit is waiting for us at the end of the problem. We don't want to stop the problem and say that the limit does not exist. We know we have to do a little bit more work because the expression is not showing us what the limit is. Okay. So 0 over 0 does not mean that the limit is undefined. 0 over 0 means our problem is incomplete and unfinished. Right? It's true that the function value is undefined because there's a hole in the graph, but the limit most times will still exist. Well, for our purposes, if we ever see 0 over 0, our limit will exist. So how are we going to work around that issue without having the graph in front of us? What we're going to do is we're going to try to factor and reduce and simplify. We're going to try to find in the numerator and denominator of our expression what's causing that 0 over 0. And then we're going to remove that 0 over 0. And if we remove it, we're going to get a reduced expression. And then from that reduced expression, we're going to reevaluate the limit. So basically what we're going to do is we're going to try to create an expression that is a similar graph without the hole in it. We basically want to create a graph without the hole in it. And if I can create a graph without the hole in it, I can make a continuous function out of it, and then I can evaluate the limit where that hole was. Okay. All right. Let's look at example A here. Example 2. Limit as x approaches -2. First steps first. This is our anchor step. We always do direct substitution, regardless of what you think is going to happen. All right. So if I plug -2 in for x, okay, what do we get from the numerator? 0. Guys, put an arrow like this. I'll talk about that in a second. Okay. What I get in the denominator? 0 as well. So this tells me that there's a what in the graph. There's a hole. The limit exists. We still have to find it. Okay. So this problem is incomplete, but we do know what's coming up. We're expecting that at the end of this problem that we're going to get down to a real number. Okay. College Board is picky about evaluating, doing direct substitution and getting a 0 over 0. So having an equal sign sometimes may cause some issues for graders. Technically, it's not equal to 0 over 0, so there's a whole debate about that, but we just know that College Board doesn't like it. So if you're doing direct substitution and if you're getting a 0 over 0, put an arrow to indicate that you're not committing to saying that this is equal to this. You're just saying to the grader that this is the next step. I'm not going to take off any points if you say equal to 0 over 0. I'm just letting you know that is, but I would like for us to kind of get into the habit of understanding that College Board, whenever they see an equal sign, they're going to look carefully on both sides of the equal sign and actually see if they're actually equal. If they're not equal, then you may lose a point on the AP exam. So the way to get around that is use arrows to indicate to the grader. I'm not saying they're equal. I'm just saying this is the next step. And yeah, this seems kind of petty, but just wanted to kind of give you a heads up as to how sometimes they grade things a little differently. Okay, so we get 0 over 0. We know there's a hole. And the hint is this denominator. You see this x plus 2 is as reduced as it can get. This x plus 2 is obviously causing a 0, which means that there's also an x plus 2 that's hiding in the numerator that's also causing that 0. So the hope is that after we factor, we can find something that we can match and reduce, and then we can reevaluate. So we're going to step to the side, and we're going to evaluate the numerator by factoring. X squared plus 5x plus 6 multiplies to be 6, adds up to be 5. What are my factors here? 3 and 2. As long as, if you're doing a limit problem algebraically, as long as there's x's left in the expression, you're going to keep holding on to your limit statement. Okay, so you have to keep rewriting your limit statement if there's still an x in your expression. All right, now what do you see? Numerator denominator shares a what? X plus 2. Let's remove it. Okay. So what's left is now we have an expression or an equation that looks virtually the same as this, just without the hole in it. And now we can evaluate the limit and pretend like this is a continuous function, or that we're basically creating a continuous graph without the hole in it, and then we're just evaluating the limit at this stage. Okay? So we're going to reevaluate the limit, and we're hoping with the hole removed that we'll get a real number. If I do direct substitution again, what do we get? Oops, I'm sorry, approaching -2, my bad, approaching -2, okay? So plug in -2, we get, yeah, -2 plus 3, which is equal to 1. And this is our limit. This is our limit. This is where the hole was, and now we created a linear version of this graph, and then we're able to reevaluate. Notice that now that the x's have disappeared, because I've plugged in the -2, there's no need for me to rewrite the limit statement. I'm only rewriting limit statements if there's x's in my expression. So just to kind of give you a graphical perspective as to what's happening, this was what the this was the graph that we were trying to evaluate the limit for. There was a hole here, and that's why we're getting 0 over 0, because we're not able to, algebraically, we're not able to get to where that y value was, because that y value doesn't exist. But then once the hole has been removed, we basically recreated this equation as this one. Okay? So the x plus 3 with the hole removed is just this equation. And then if we do direct substitution, if we plugged in -1, now we're able to, sorry, if I plug in -2, I'm actually able to get to that real number of 1. So we're basically creating a different version of the expression so that algebraically we can get down to a real number. All right, let's look at part B. Limit as x approaches 1. What's our first step? Direct substitution, right? Even if you feel like, oh, I want to factor because it looks like it's factorable, don't do anything else until you've done direct substitution. It feels like an extraneous step. It's like, well, if it's already factorable, why do I need to go through direct substitution? It's going to help us anchor our steps, okay? Because we can't assume that there's a hole in it. We always want to do direct substitution because we don't know what the graph is looking like. Okay, so direct substitution, 1 in for x, numerator, we get what? 12. Denominator, we get 0. Is this defined? This is undefined, but it's different than 0 over 0. 0 of 0 tells that there's a hole in it. This tells us that the limit exists, then we keep going. Does anyone know what this is telling us about what the graph is looking like? There's a what? There's a vertical asymptote. There's a vertical asymptote at x equals 1. And what do you know about the limit if we're approaching a vertical asymptote? Doesn't exist. So if we get this, we're not going to go and factor because there's nothing that we can do to cancel anything out because there's no hole, right? It's a vertical asymptote. This numeric situation is basically telling us what's happening. And that's why direct substitution is so important, because it can kind of give us an idea what we're dealing with, right? Are we dealing with a continuous function? Are we dealing with a hole? Are we dealing with a vertical asymptote? If we jump into factoring and trying to go through a problem, then you're making an assumption that may not be true, right? So your direct substitution is going to help you decide which category you're dealing with, and then you can take the next appropriate step. So here, the limit doesn't exist. We may go a little deeper into this and talk about, are the arrows headed in the same direction? But for now, we won't do a subcategory just yet. We'll just say it does not exist. Okay, part C. We have an expression approaching a real number, x approaching 2. First steps first. Direct substitution. Replace every x with 2. Numerator, we get 4 plus 10 plus 6. 20. Denominator, we get 4. Is that going to lead us to a real number? 5, right? So there's nothing more to do, right? If I have a real number, there's no need to factor, right? Because I already evaluated, I've gone down to a real number. There's no more work that needs to be done, even though it looks like, oh, maybe I need to factor and reduce, but this is telling us that the limit exists. There's no additional steps we need to take. Okay, part D, direct substitution. Even though it looks like we can factor, don't skip that first step. Okay, numerator, we get 0. Denominator, we get 4. Okay, what does that mean? It's 0. That's a real number. So that's our answer. And now that we've seen these different variations of 0, let me kind of summarize what happens when we see zeros, right? Just because you see a 0 doesn't mean that it's going to mean one thing or another. It depends where that 0 shows up. So let me give some reminders in terms of distinguishing variations of 0. Okay. If you get a 0 over 0, that's called indeterminate form. That means there's a hole. That means you keep going, that there's a limit. There's a real number to be found. We just have some work to do. If you get a non-zero over 0, let's say 12 over 0 or 5 over 0 or negative 3 over 0, that is indicating to you that there's a vertical asymptote and that the limit does not exist. You can visually see what could be happening, right? There's a dotted line, and then the arrows are either pointing both up, they're both going down, or one's going down, the other's going up. But we know how a graph can behave around a vertical asymptote. If we get a 0 over a non-zero, like 0 over 4, 0 over 8, 0 over 10, that's a real number. We want to stop and produce that as an answer. So let's not get confused between these variations, and that if we see zeros showing up in our evaluation, that we know which category that we're dealing with, and then we act accordingly. Okay, so let's try each, and then have you guys try one. We'll go through the answer, try two, go through the answer. Okay. But remember, direct substitution is always your first step. Let's not assume anything. Don't let the fact that something looks factorable throw you off and causes you to try to do all your factoring steps, right? We don't know what's going on because we don't have the graph in front of us. And this is a way of gathering information. What'd you guys get for number one? Numerator, we get let's get 2 minus 1 minus 3, which is -2. Denominator, we get 0. So this is telling us what? Vertical asymptote, limit does not exist. Down the next week, we may do a little bit more work with this. We may decide, wait, are the arrows, there's the vertical asymptote, but are the arrows headed in the same direction? Can we create a subcategory? But we'll learn that skill next week. But right now, let's just give it a generalized answer and say the limit doesn't exist. We're not going to deal with subcategory just yet. Okay, number 2. I got 13 over 1. Is there anything more that we need to do? That's a real number, right? So that's my answer. That's my limit. Okay, number 3, direct substitution. What do we get? 0 over 0. This tells us what? There's a hole. Does limit exist? Yes. We have to find it though. The simpler side is going to give you a clue because the x squared minus 1 looks like it's factorable, but this x plus 1 is also giving you a clue because you know that this x plus 1 is causing the 0, which must mean that there is an x plus 1 that's also hiding in the numerator that's causing the 0. So ultimately, you're trying to cancel an x plus 1 that's going to appear in the numerator after we factor. So even though we're not doing anything with that x plus 1, that is still a helpful hint. You know what to expect from the other side. You already know what's going to happen. You're going to find an x plus 1 above and below and try to cancel that out because you know that's causing that 0 over 0. Okay, we know that we got to do some work. We know that we haven't, we're not done with the x's yet. So I'm going to rewrite my limit notation. X squared minus 1, this is factorable, right? Difference of squares. What does x squared minus 1 factor out to be? X minus 1, x plus 1. And just like what we suspected, we're seeing an x plus 1 appear, and we can try to take those out. So we see there's a hole. We're able to remove it. Our goal is to find the limit. We're trying to find a real number, so we have to reevaluate. The hole has been removed. Hopefully, this is now going to give us a real number. What do we do with, what do we get from direct substitution? We get what? -1 minus 1. What do we get? -2, yeah. So notice that my variables are gone. There's no need to write your limit statement. You're only rewriting your limit statement if you're having to write your x's down again, which means that if you're trying to do some cleanup with your expression, you're going to have to rewrite your limit statement. But once your variables are gone, just leave your, then you can drop your limit statement, your limit notation. All right, number 4. It may look factorable to you, but we don't want to skip the first step, right? Let's gather information. Let's do direct substitution. All right, what do we get? -3 over 0. What does that tell us? Vertical asymptote, which means that the limit does not exist. So even though this all looks nice and factorable, we don't do that step, right? Because we know that no matter what we find, there's not going to be a common factor that we can cancel out. And there's no hole to worry about. There's no limit to worry about. We already know what our answer is. The limit doesn't exist. So that's why it's so important that we do direct substitution first, because if we make assumptions, sometimes we may go down the wrong path. Okay. Number 5, first steps first, direct substitution. Okay. Numerator, we get 0. Denominator, we get 0. Therefore, what? There's a hole. We keep going. We know that there's something that's blocking our ability to find our limits, but we know the limit exists. And both sides require factoring. So we're going to factor both numerator and denominator. Because there's more work to do, we know that there's going to be x's that we still have to rewrite, which means we're going to hold on to our limit notation. We're going to rewrite our limit notation. Trinomial factoring here. Multiplies to be -6, adds up to be 1. What do we get? 3 and -2. Denominator, x squared minus 9. Difference of squares. 3 and -3. All right, we see the cause of the hole here, x plus 3, x plus 3. Cancel those out. Now that we have an expression without the hole in it, we should be able to now do direct substitution and get a real number. So now we reevaluate. Remember, your goal is not to get to the reduced expression. Your goal is to get down to a number. Your goal is to get down to a limit. So we don't want to leave our answer in this form, right? There's more steps to be done. It's just direct substitution. All right, numerator we get. Over x minus 3. And what do we do with those x's? Direct substitution, right? Direct substitution again. -5. Denominator, we get that's a real number. We can reduce it to 5/6, and the limit exists. So if you were to look at this graph, both sides of -3 is going to get closer and closer towards that y value of 5/6. All right, number 6. All right, first steps first. Direct substitution, right? 0 over 0. Okay. We can't do anything in the numerator, but we can do something in the denominator. So the one that we can, the side that is easier, that is reduced already, that's kind of giving us a hint. That means there's probably some variation of 5 minus x that's hiding in the denominator that's causing both sides to produce a 0. So we know there's factoring work that needs to be done. Make sure you rewrite your limit statement. Difference of squares, x squared minus 25, factors to be. Yeah. Now we know that this 5 minus x and x minus 5, this is what we're trying to target, right? We're trying to find a way to get these two to cancel out, but they're not quite exactly the same. I mean, they're close. But is there anything that we can do to make this a better match? Can I factor out? Because these are just off by what? -1, right? So what if I just factor a -1 out of this? Then that means I can force these two to change the signs. If I can change both these signs, that will match the signs of this right here. So if I factor a -1 out, I get -5 plus x which is now a better fit. Okay, -5 plus x, same thing as x minus 5. Now that I have a better fit because of factoring, I can cleanly cancel this out, but I'm keeping track of that -1 that is causing that difference. Okay, what's our final step? Direct substitution, right? We know that whenever we see this, our goal is to get down to a real number. We're not trying to get down to a reduced expression. We're trying to get down to a real number. So make sure that after you cancel out your expression, that you're still doing direct substitution as your final step. -1 over 10. Do we feel okay about these problems? So keep in mind, right? Direct substitution. We're going to see more. We're going to see more variations of problems that are going to produce 0 over 0, but you're going to be tempted to want to go down your steps because we're going to go through more types of problems that require cleanup. But let's not assume anything until we get that 0 over 0, right? Because sometimes your problem is nice and factorable, but if you do direct substitution, if you get a real number, then we stop, right? There's no need to go through all this factoring steps because you know that all your cleanup is in the hopes of getting a hole to be removed. So if there's no hole to be removed, then we're just doing additional steps that we don't need to do. Okay, so always first steps first, direct substitution. Don't let the expression cause you or distract you from doing other things first. Okay. Let me see if I can go through. There are 2 other types of problems that also produce 0 over 0, but they require a different set of skill to get the holes to appear and to cancel out. So on page 7, let me go through. This is called simplifying using the conjugate method. So sometimes we have radicals in our problem, and it may require us to go through something called multiplying by the conjugate. So the conjugate is basically the exact same term as what you see with the radical. The only thing that you change is the sign in between. So if I had a plus root b, and I'm trying to find a conjugate for that a plus root b, it's going to be a minus root b. Okay. And the reason that we want to involve multiplying by the conjugate is it allows for the radical to go away, and it allows for one side to clean up in a way that can help us identify the whole easier. So we always copy the exact same expression as we see in the problem with the radical, but the only thing that we change is the sign between the 2 terms. All right, example 1, limit as x approaches 4, 6 minus root x plus 32 over x minus 4. Again, we don't want to assume anything. What's our first step? Direct substitution, right? So replace every x with 4. What do we get in the numerator? 4 plus 32 is root 36 is 6. 6 minus 6 is 0. 0 over 0. Okay, so now we know there's a hole in the graph. Now we know that, okay, I need to do some more work with this because I'm looking for a number, but right now it's showing me incomplete status. Okay, we know there's more work to be done. This x minus 4 is a big hint because we're not going to do any work with x minus 4, but this does hint to us how we want the numerator to eventually show. We want a numerator to show an x minus 4 because we know there must be an x minus 4 hiding. Otherwise, we wouldn't be getting a 0 up in the numerator and 0 in the denominator. Okay, so that's a hint that we're hoping that an x minus 4 will appear when we do our cleanup with the numerator. All right, let's rewrite our limit expression. I'm going to rewrite my entire expression here. So we need to multiply this by something in order to hopefully get that radical to disappear. And we're going to multiply by the conjugate of this numerator to produce a different variation of that numerator in the hopes that an x minus 4 is showing up. Because right now, an x minus 4 is not clear where that is in this problem. So what's the conjugate of my numerator here? X plus 32. Now, you see there's multiple signs within your expression, but you're only going to change what's between the radical and the term. Don't change what's inside the radical. This is already set in stone. When you create your conjugate, you're only changing what's between the two terms. I want to basically multiply by 1 so that I'm not changing the overall value of my starting expression. So whatever you create as your conjugate, make sure you copy that exact same thing to the other side of your division line. Good so far? Now here's the cleanup. We're going to expand and multiply this out. We're only going to multiply the numerator out. We're going to leave the denominator alone because the x minus 4 is already showing what we want to cancel out. We don't want to lose that x minus 4 when we expand it. So it's just a numerator that we want to expand out. Now, when you're multiplying your conjugate terms together, you only have to worry about your first pair and your last pair because your middle pair will do what? Cancel out. So that's nice. Okay, so just the first pair, the last pair. 6 times 6 gives us 36, right? What's the 2 square roots going to do? What's square root times square root? Yeah, just what's left. Just x plus 32. Now, what's a negative times a positive? Negative. So if I am having to put a negative with multiple terms, what do we have to be careful about? We got to do it with that negative. There's multiple terms here. We got to distribute. So we need to protect that x plus 32 with a set of parentheses. Otherwise, we're going to forget to distribute that negative through. So that's a little bit little subtle that we have to watch out for. Okay. Now, I'm skipping the middle steps here because the middle steps, the middle terms, negative 6 root x plus 32 and the positive 6 plus root x plus 32 will just cancel out. I'm just left with my expression without the radical, which is what we want. Denominator, go ahead and rewrite. All right, numerator, I can clean this up, right? 36 minus x minus 32. I'm distributing the x through, the negative through. What's 36 minus x minus 32? Okay, good. Again, leave the denominator in factored form because the x minus 4 is already showing what we want to cancel out. We don't want to lose that x minus 4 into the expansion for that inside for the parentheses or in the denominator. So we're getting close, right? We know that there's a hole. We know that we want an x minus 4, but this is not quite perfect yet, even though we know that this is eventually what we do want to cancel out. What can we do to make this to be a little bit better fit here? Factor what? A negative 1. Notice I'm writing my limit statement repeatedly because I'm still having x's in my expression. Now what can we do? Right. We know there's a hole in the graph, right? We know there's something that we need to cancel out. Now the x minus 4 can reduce. We can't stop yet, right? We're trying to find a limit. We're trying to find a number. What's our final step? Replace all the x's. Sorry, replace the remaining x with what? With 4. Notice all my x's have disappeared. There's no need to rewrite your limit statement. Now you're just down to trying to clean this up. What's 4 plus 32? What's root 36? 6 plus 6, 12. So there's my answer. Whenever you get a 0 over 0, your goal is to try to get down to a number. You know that there is a number, a real number waiting for you at the end of the problem. We just have to make sure that we know how to get to it. There's one more thing that we haven't gone through, that's common denominators. We'll do that tomorrow. Your homework, if you look at it says page 99 to 102, 31 to 49 odds. So that's going to be on your exercise page. Should be right after. Here we go. Page 99 to 102. 31 to 49. So 31 to 49. Okay. So I'm going to send out a reminder this afternoon that I'll be checking homework tomorrow. That I'm going to ask you to put this on a separate sheet of paper. And I'm also going to send a link to my my Unit 1 limits page, which has where I work out the solutions as well, so you can double check your answer. Okay. All right, come get your phones. Guys, we're on B schedule today, tomorrow, and Thursday.